Here for our first of the semester college webinar. Our speaker today will be Dr. Ashanthi Maxworth, who's currently Assistant Professor in Electrical Engineering at University of Southern Maine. So Dr. Maxworth is originally from Sri Lanka. She obtained her bachelor's degree in University of Moratuwa. Then she obtained her graduate degrees, both MS and PhD at University of Colorado, Denver. So she's one of our proud alumni, and we're very proud to have her come back and share her knowledge. After graduating here, she did a postdoctoral fellowship in the University of Saskatchewan in Canada. She's currently assistant professor in University of Southern Maine, and she has been honored both by NASA and by the IEEE for her many accomplishments. So without further ado, I'll turn the floor over to Ashanthi. Again, what I said, if you have questions during her talk, she welcomes that. You can also use the chat or leave your questions to the end. So Ashanthi, the floor is yours, and thank you again for joining us.
Yeah, thank you, Professor Galkowski. And then this is my graduation picture. So I was Dr. Galkowski's first PhD student. So I gave it in my office. So I'm happy to be presenting, and then since it's a very broad audience in college, so I picked this topic, and you are welcome to ask any questions anytime. So let me share my screen. There you go. Yeah, so I hope that you can see the slide advancements and so on. So this is a new project. It's called Alpha. So Alpha stands for Active Learning Platform for Hands-on Antenna Designing. So as Professor Galkowski mentioned, I'm right now at University of Southern Maine in Portland, Maine. The engineering faculty is located in Gorham, Maine, which is about 15 minutes away from Portland. And I actually got my PhD at University of Colorado, Denver. So this is like, like coming to Colorado, usually it's like going home for me. So, and I'm happy to present via Zoom at this time for all of you. So if you have any questions, please ask me at any time. So as I mentioned, this is one of the broad topics, and the reason I picked this topic, as I mentioned earlier, is because I know most of you are from different disciplines, and I want this topic to be suitable for all of you. So that's the objective of this. So I will actually introduce to you why I developed this. So I'm answering the question of why before going into what it is, and then how I implemented that, and the feedback I received from students over these years, and some of the future steps. So this is an active learning technique. It's an active learning practices that I practice at University of Southern Maine. And as I go more into the presentation, I will give you an introduction about the student body, or the composition of the student body, and the courses that we teach here. So first of all, I know you are from different disciplines, so let me tell you why I developed Alpha. So Alpha is this acronym. I like the term Alpha. I like the sound of it. So therefore, I thought, okay, I need to come up with a cool acronym. So when I first joined the University of Southern Maine, so my area is electromagnetics. I was Dr. Galkowski's first PhD student, and I taught ELEC 3133 electromagnetic fields, or fields 1 at CU Denver for about 3 or 4 consecutive semesters, starting from fall of 2016 until the fall of 2017. So I think it was 3 consecutive semesters. So my expertise is in electromagnetics, and my PhD was in numerical ray tracing of the magnetosphere. So Maine is one of the states, it's a NASA EBSCO state, where the space research is not very developed yet. So I'm one of the very few people who are doing space research in the state of Maine, and within USM, I'm the only one who has expertise in electromagnetic fields. So when I was joined USM, so I was bound to teach 2 required courses. One is ELE 351, which is electromagnetic fields, which is a required course for all electrical engineering students. And then we have quite a good number of mechanical engineering students who are taking electromagnetic fields as an elective, because some of them, they would like to go for jobs in electromechanical engineering. And also I was bound to teach communication engineering or communication theory. And I was required to come up with a technical elective as well, which is so that anybody who completes 351, they can take a course after 351. So I thought, okay, what would be a cool elective for that? So I thought, okay, I'll go with antennas. I learned antennas from Professor Gokowski, and I really enjoyed that class. So I thought, okay, this is a good class that I can that I should develop here. So ELE 452, that's the code name. So ELE 452, that's the code for antennas. So this is a new technical elective I introduced for all engineering students. And last semester I had the majority of electrical engineering students, and then I had about 10 mechanical engineering students as well. So 552 is because sometimes students can take the course in the graduate level. So because University of Maine system is quite similar to University of Colorado system. So the University of Maine Orono is like CU Boulder, and then we have other campuses, like for an example, University of Southern Maine is like CU Denver. We are quite smaller than CU Denver, but we are located within the city, and then many students, they go for jobs in Portland as well as out of the city, out of Portland as well. So this is a senior and a graduate level course. So that's the basis of the basis of antennas. And then like why I chose antennas, that's because as you can see in these pictures, like RF engineering or radio frequency engineering is a big industry in the USA as well as across the globe as well. Like I'm originally from Sri Lanka, as Professor Gokowski mentioned, and right now we are going through an economic crisis. So everything is becoming expensive except the communication cost, because everybody like your cell phone bills are actually getting cheaper because of the competition between service providers. So antennas are everywhere. It's a part of communication engineering. It's a part of RF engineering. It's a part of biomedical engineering. And it's a part of every other form of engineering, like in robotics, in electromechanical engineering. So antennas are everywhere. There are different sizes of antennas. There are different types of antennas, and there are different material that people actually make antennas with. So it's now a part of material science as well. So I thought, okay, like if I'm offering an elective, antennas would be a good choice for me, because the people who are taking, the students who are taking, they are ready to graduate. They are in their senior year, or some of them are graduate students. And I thought, okay, in this course, I can give them a lot of practical applications. If they have if they want to go into biomedical engineering, they can find a good number of applications where they can use antennas. If they want to go for communications engineering, then antennas are used everywhere. And if they want to go for if they want to go for defense applications, military applications, or if they want to go for any other form of engineering, still the knowledge they're gaining from this class will be useful in their case. So therefore I thought, okay, this is a good choice. I will actually teach this class, and this is the first time because at USM, as I mentioned, I'm the only one who is actually teaching electromagnetics courses. So therefore I thought, okay, this will give me a good foundation. I'm teaching ELE 351 electromagnetic fields, and this will be a course that they can take after taking 351. And when they go for a job, or when they go for graduate studies, they can directly apply this knowledge to whatever the field that they're dealing with, because now space is another field that state of Maine is trying to promote, as well as sensor development. So there are lots of applications. So that's how I chose antennas. So, and then in this antennas course, we are using the textbook. This is the same textbook we used at CU Denver as well, and at CU Boulder and many other universities. They used this textbook from Dr. Constantine Balanis. And so we are covering quite a lot of topics. We are starting off with antenna parameters and different types of antennas, starting from very small infinitesimal dipole and monopole, loop, antenna arrays, broadband antennas, and then traveling waves. So we are covering a broad range of antennas in this course. So I was excited about the course. So I thought, okay, like I'm excited, and then I want to make sure that my students are equally excited as I am. And they, because my goal was that they gain some knowledge that they can directly apply for their future jobs or in their future studies, or maybe to pick something at home. So something like that. So so they gain something that they can directly use right after taking this class. So, but before moving further, if I go any further, I want to mention, like, as I mentioned, like I developed this new model for my course. So therefore, like everything I'll be presenting in this presentation, they're based on my experience teaching this course in this new modality. And I'll be referring to this course antennas, ELE 452 antennas a lot in this presentation. But I but I want you to use this course in your engineering courses. And I mean, I would like to see that people apply this model into their courses and I want the students to apply this for their courses and then improve on it, improve the model as well as improve their experience. So this model I developed, it is with the same name, Alpha. It was published in the National Teaching and Learning Forum, and you can there's a link here. I'll share the presentation after that, so you can download it. So this was developed during the pandemic because I joined University of Southern Maine in the fall of 2020. So it is officially 2 years now. So I developed this during the pandemic while we were teaching in the hybrid mode. And I was teaching this course at 8 o'clock in the morning last spring. So spring in Maine, it's a pretty cold time. So many students joined online. So I wanted to take that aspect into account as well, because it makes a difference when somebody is in front of you versus when somebody is joining via Zoom at 8 o'clock in the morning. So that we want to make sure that they are engaged in the process. So although I am referring to my antennas course, although I developed this active learning model for my antennas course, that doesn't mean this can be used only for this course. By now, I have told you like why I chose this course and then why I developed, or in other words, like why I developed this model. But I want to see this being applied to all the other engineering or as many as possible engineering courses. So one issue, so I chose antennas to offer as my technical elective, and I want to make sure that this is a course that students are interested in, because like within the engineering department, they have many electives, so that we have to make sure that we have enough number of students that we can attract so that we can run the course. So one of the prerequisites for this course is electromagnetic fields. So there are many challenges when we are developing a course like this, because almost all the engineering courses, so I'm a mathematical person, so seeing math in a course doesn't scare me. But it's not the same when it comes to all engineering students. Some people get easily scared off by math. And some people, they love math, so they don't mind seeing a good amount of math in their courses. And some students, they think engineering and mathematics, they are two separate fields, they should not be together. But the truth is, when it comes to engineering is the applied field of physics and math. So if you are trying to develop something new, if you are trying to go for the design level, then there's a high chance that you have to deal with a good amount of math so that you can develop the application. But I expected these challenges because every time, so I have been teaching electromagnetic fields for a long time, since 2016. So every time there's at least one student who writes comments like, this is very mathematical. There are a lot of calculus, because everything is based on calculus 3 or calculus C. They need more hands-on examples, although we do some in-class examples about how to apply the theory. They always request more hands-on examples and more examples on how to apply the theory. Or like some people might say like, okay, why do we need to learn all these math and things like that. So some comments are, sometimes you get like good comments, and sometimes you might think the student did not understand your viewpoint. But either way, I knew that if I'm teaching antennas, which is a post course for electromagnetic fields, I will have to face these challenges. They will have trouble with math because antenna designing can have a good amount of math. And they will have trouble visualizing things like radiation patterns and so on. They will ask for more hands-on examples, and they will ask examples on how to apply the theory. So in order to prepare for these challenges, that's why I developed this new model. So that's why I developed Alpha. Alpha is this cool acronym I came up later, but I thought, okay, what if I combine all the active learning techniques, or as many as active learning techniques as possible as I can fit into one semester, and then develop this one course so that I can avoid some of these, or I can face some of these challenges with my head held high. So are we all good with that? Like why? What is the motivation? Like why I did that? So now I will tell you what is Alpha. So Alpha, the acronym stands for Active Learning Platform for Hands-on Antenna Designing. It has three components. One is the human factor. So human factor is the instructor and the students. So I am actually a fan of the traditional, it's called traditional brick wall teaching, where the instructor teaches the student. And I think having somebody or doing a live lecture is more effective than doing a video lecture. So that's one factor. One aspect of that is the human factor, me as the instructor and the students. They can join in person or they can join via Zoom, but I will be teaching in class. The second component is the virtual experimentation. So this is the simulation part, because I want to give more hands-on experience to the students. So simulations and videos, so those are virtual experimentation where they are allowed to make errors. If you make a mistake in a software, no issue. You can delete everything and restart. It's different than building something in a lab and then breaking something. When it comes to simulations, you are allowed to break as many times as you want. So I merged a lot of simulations into the course. And also there are some real experimentations such as antenna assembly and taking measurements outside and designing and things like that. So altogether in this Alpha platform, it's hands-on. So therefore, there are three components: human factor and the virtual experimentation factor and the real experimentation factor. So this is how a typical syllabus looks like. So in other words, so the active learning techniques I combined. The main one is the virtual experimentation, where we do a lot of simulations in class. And also there are some team-based learning where they have to build things as a group, not larger than 3. And also all the exam questions are problem-based, where I give them a problem with constraints and requirements, and they have to come up with a design. And some of these questions are quite open-ended as well. And also I gave them 2 case studies. Instead of submitting a report, they had to submit a video presentation, and I'll talk more about this later. So in here, you can see a typical syllabus. So in this case, like we give the topic and I give them what is the virtual experimentation that, or the virtual experiment we do in class that day. And so there are like, we give the introduction to antennas and gain, the basic parameters and then different types of antennas. And as we go into each topic, there is a virtual experimentation associated with it. So instead of direct learning from me, what they can do is so I teach for a little while and then we switch to HFSS and then do the antenna modeling. And then visualize everything. And I explained while we are obtaining results as well. So at the beginning, I gave them a lot of help. I did simulations with them. But as we move further, I reduced the help I was giving. And there are traditional exams as well, because I think exams are a good way to test the knowledge compared to other methods. So a typical assessment scheme. So this was the assessment style that I used in this course. So they have I mean, I'm famous as one of the high maintenance professors at USM because I make them work. So exam 1, which is typically in the 6th week of the semester, exam 2 is around the 12th week, finals exam is in the 16th week. And I assign homework assignments, and then we do a lot of virtual experimentation in class. And then there were 3 real experimentations. And then these case study video presentations, they are actually based on some of the case studies that I gave, because I want to give them more examples on how these things are being applied in a larger scale. And I'll talk more about those later. One thing I want to emphasize in this one is that as you can see, like exams don't contain, like they don't have a heavy weight. Exam 1 is only 15%, exam 2 is only 15%, and finals exam is only 20%. So those are actually lower weights compared to like 22% and 30%. I did that on purpose for this class, because for the EM Fields class, the exams have heavy weights. But in this class, it depends upon the body of the students, because they are all seniors and grad students. So when it comes to concepts, they have a pretty strong grasp of concepts, because that's why they chose this class. That's why, I mean, it's an indication they liked 351, so they want to learn more about it. So therefore, in this class, it's one of the classes where there are lots of assignments, and each one has a smaller weight. So if you have test anxiety and if you're scared of exams, exams might not be your thing, because you might have a good knowledge, but at the moment you sit for the exam, you might lose it altogether. So therefore, in this course, the exams don't carry a heavy weight. If you can do well in the exam, great. But it's one of the classes you have like lots of small assignments, so that if one type of assessment is not your type, still it's fine. Still, you can cover it up with another form of assessments, because there's a variety of assessments in this course.
Hey, Ashanti, one question that came up in the chat on this is the comparison of real versus virtual experiments. Are the real experiments based off the virtual ones? Are the real ones with actual hardware? Could you comment maybe on that?
Yes, yeah, because the virtual experiments, we are using HFSS for antenna modeling, and then we observe radiation patterns. In real experimentations, they had to build the antennas. So we actually build 2 types of antennas. So we build, so they did a Yagi antenna assembly at one point, and then they all designed the patch antenna. Another one, so where they had to use circuit like PSpice or Eagle or software like that, and they design it. So some of those are typed, because for an example, I will be going more into the real experimentation section in a later slide, but virtual experimentations are pretty much every week, every class we did some simulation of an antenna. But real experimentations, we did only 3 antenna building,
And those 3 real ones were also, I guess, a subset of the virtual ones, right? But
exactly. Yes.
Okay.
Yeah.
And for those non-EEs in the audience, the Yagi antenna is like the old style kind of TV antenna, you know, with the one pole and the other crossing it. A patch antenna is kind of a small antenna, often, you know, low profile. You often see it in GPS antennas and things like that. And, you know, a lot of cell phones also have variations of those kind of patch antennas. So.
Yeah, so I'm going more detail into each component. So in this case, like human component is the traditional classroom teaching. And one thing I implemented this one is that at some point, like I tried to implement the flipped classroom approach, where the students are required to watch a video before coming into the class. But that approach was not successful because the reason being, like I know at CU Denver also, there's a diverse student body. At University of Southern Maine, especially in engineering, we have a healthy balance of traditional and non-traditional students. So they have like everybody is working outside, and everybody, like some students, they have families. So they have a lot going on outside of classroom. So I realized, okay, the only dedicated time that I can get from my students is the time that they are sitting in front of me. At the moment they leave the classroom, I cannot guarantee that they watch my video. I cannot guarantee that they are doing the homework I assigned them to do. So therefore, I thought, and in the flipped classroom approach, it requires that students do some outside classroom work before coming into the class. And if I have at least one student who has not watched the video, then that actually delays the entire speed of the class. So that's why I thought, okay, like the flipped classroom approach might not work for my student body because they have a very limited time outside the classroom. So therefore, I need to maximize the, or I had to maximize the efficiency that they spent inside the classroom. So in this classroom field, because like so we meet the class. So the course meets twice a week, and then we get 2 days. So on one day we meet for 75 minutes, and then on the other day we actually meet for 85 minutes. So the days that we are meeting for 85 minutes, those days are ideal so that we can do virtual experimentations. So during this time, I introduce the basics, and then I make the segue to the virtual experimentation. Before going into the virtual experimentation, I tell them, okay, like in this class, we'll be dealing with the horn antenna, and then I'll show you more examples. And in this time, we are dealing with this type of an antenna. So, and these are the parameters, and what are the applications, what are the pros of this type, what are the cons of this type, and what are the main applications that people use this type, and then what are the drawbacks and why people try to move away from these antennas if they have issues and so on. So during this time, I introduce the basics, and then kind of make the path for the virtual experimentation, so that in case they make a mistake in the virtual experimentation, they know how to fix it. At the same time, they should know how to interpret the results, what is the expected result, and if they make a mistake, how the results would change and how can they fix it, and so on. And all the lectures are recorded and uploaded as well. I did that. I'm kind of doing it this semester as well, because it was an 8 a.m. Class, and then many students joined via Zoom. So sometimes if they miss a step later on, they can go back and then review. So exams wise, as I mentioned, this class had 3 exams, like one close to the midway of the semester and one towards the end of the semester and one finals exam. So I gave exams all open book and open notes, because when it comes to antenna design, there are lots of equations. And as I remember, when I took antennas at CU Denver, our exams were open book as well, which was actually very practical, because there's no way if, somebody can remember all the design equations that somebody needs for this class. So I gave open book and open note exams, and most of the questions were design type questions. So there were constraints and there were requirements, and they had to come up with their own design to fulfill these requirements and the constraints. And some questions where they had to apply design equations and then come up with their answers. So one thing you might have heard this as well. So when it comes to engineers, you might not know everything, but you have to know where to find everything. So they have to refer to the textbook. They have to prepare their note sheets prior to coming into the exam, because otherwise they might not have time to flip through the entire textbook and then see, okay, where are these design equations? Because as engineers working in the field, they have to make sure that they produce the results within a given time frame. So therefore, although the questions are design type, although it is open book and open notes, they have to come prepared. They have to know, okay, what should I apply in this particular case? And if they apply the wrong equation, then they get a wrong result, and that's not what your employer might need. So the questions are design based, so they'll have a design type of questions, and then usually a typical exam contained about four questions where they had to finish within 75 minutes. So, so that's the exam component of it. And then the other one, it was the virtual experimentation part. So we used HFSS, and another thing about the student body at USM. So we are primarily an undergraduate teaching institution. Our graduate program is still being developed, so it's still growing. And right now we have a strong drive towards research, but the primary focus of the university is teaching. So many students, right after graduation, they want to go for jobs. And very few students would like to go for graduate studies because they are not familiar with that concept. So right after graduation, they want to at least work in the industry for at least 2 years. So like one reason I promoted HFSS is because I thought, okay, many students who are taking this course, they are graduating pretty soon. And like everybody in that class graduated by the end of last spring. So it's another added qualification for their resume. Okay, like I know HFSS, I have the proficiency in HFSS. So we did a lot of simulations, and it actually made the class a little like, for an example, as I mentioned, I had short 75-minute class periods as well as 85-minute class periods. So those 85-minute class periods were ideal for this virtual experimentation, so that they could visualize, okay, if I build this type of an antenna, what is the radiation pattern? And then if I tweak the parameters, if I increase the length, if I decrease the length, how the other parameters like the gain and the electric field, how those parameters change. So those things they could visualize right after learning that concept. So I introduced them, okay, this is what we are going to do today. And then these are the parameters, and this is how you design an antenna to match the frequency and everything. So then they could actually simulate that and then see how the parameters or how the equations would actually how they affect the actual antenna design. So for every class, I actually produce these worksheets. So these worksheets are step-by-step guidelines because many students, they are new to this software. And I had some students from electrical engineering and some students from mechanical engineering. At the beginning, they were following the simulations with me. But then at some point, if the pace is different, if they miss a step, they need to have something to go back and then fix that one. So I prepared these worksheets. So altogether, I have 10 worksheets prepared for this course, and all those worksheets, they have step-by-step guidelines. So they actually enjoyed these step-by-step guidelines because so that they can follow along in case they miss a step. So virtual experimentation, since the campus is paying for HFSS, and if we break something, that's still fine, they can always restart. So we did a lot of simulations with HFSS where they can do a first-hand visualization. And one thing is, like, when you are offering a class via Zoom, one issue is sometimes the instructor has no idea whether the students are engaging or not. So they had to use the class time to do the virtual experimentation, because at the end of every virtual experimentation, they had to upload their results to Brightspace. Brightspace is our learning management system. So they have to engage in class. If they make a mistake, they can always ask me, or they can go back to the worksheet and then fix their error. But they have to upload the results pretty much at the end of the class. And I actually gave them until the end of the day if they ran into any technical difficulties. They don't have infinite time to do that, because this is how I kind of got the attendance, and this is how I made sure that they did the virtual experimentation together with me, because while doing the simulation also, I explained things. I was explaining things like, okay, now change this parameter, now you will see the gain increasing, things like that. So all those things they could like they can get they can absorb that content if and only if they did the simulation with me. If they just watched watched me doing it uh, as watching a movie, they will not be able to upload it. So these links, they disappear after the day is gone. So they had only a limited time to upload the results. This is to make sure that they followed along with the class, because everything, like, it retains in our memory for so long. So you might learn one concept today, and then as long as you visualize it, and then you did the simulation, and then you comprehend it within the same day, then your brain keeps it in the storage. But if you think, okay, I can do it next week, it might not, because next week you have more work. So all these virtual experimentations, they had to do it and then upload. It is to make sure that they actually proceed with me, as well as it is to make sure that they attend and then engage in class. So for the real experimentation, there was a question. So this was actually one of the Yagi antennas. So I bought about 8 kits of these. So these are so this is the antenna that that Dr. Gurkowski mentioned. Like back in the day, like we had these as TV antennas, and in Sri Lanka we still used Yagi antennas. And this is like one interesting story is that so in Sri Lanka we have lots of monkeys, and during the season where the like bananas and mangoes, there are monkeys jumping from roof to roof, and then they always shake these antenna towers and then rotate the antennas. So, and these antennas, like they have they are not radiating in all directions. There's a narrow, like a strong, there's a strong there's a directional beam pattern. So therefore, like these ones, like you have to align it in the right direction, otherwise your TV reception goes away. So these are the Yagi antennas. It's a patented design, so by two people. And yeah, so they assembled these Yagi antennas in groups. And then I have pictures of some students. They just went outside. So it's Maine in the spring. So we had quite a bit of snow last semester. So they all went outside, and then this is actually Danesh. Danesh had a transmitter. He has an amateur radio transmitter. These antennas were operating at 220 megahertz, and then you can see the spectrum. We used a spectrum analyzer to see the signal spectrum. And then so in these pictures, I have some students who recently graduated holding antennas, and they enjoyed just going outside and then turning the antennas in different directions and then see how the signal reception changes. So this is one of the ones that we built. So the Yagi antenna. The other one is the patch antenna right here. So these two students, Jesper and AK, they put their names, they put their faces, into their design. So patch antennas, they are pretty small, mostly used for biomedical applications nowadays, as well as there are quite a few applications, like your cell phone has one, and then all the small devices, they have patch antennas. So it's more like so all these are copper patches. That's why those are patch antennas. And then this one, I let them go wild. I just told them, like, you can come up with your own design and then send me the files, and then we'll get those manufactured. So they actually, so different groups, they came up with different designs. So this is the design made by Jesper and AK, and then they actually designed these antennas. So this was another real experimentation that they did in class. Because based on the time, I couldn't fit so many. And also I want to make sure that like these real experimentations are something, because we need to have sufficient amount of funds as well to get these manufactured, to buy the antenna kits, and to buy the equipment and so on. Another important one was the case study analysis. Like they did two cases. One was like these ones I just I asked them to refer to these web pages. So these are all very large arrays, and then do a study, like dig deeper into the properties of that. So, and at the end, they had to submit a video submission. So students enjoyed submitting a video presentation than submitting a report, because this is another teaching thing I learned, is that it's easy for somebody to write about something they don't know, but it's very hard for somebody to explain something they don't know. So therefore, that's why I asked them to submit video presentations than writing a report. And it turned out that some of them, they exceeded my expectations. They did a lot of research on some topics. At the same time, they enjoyed preparing a video more than writing a report. So I got some very good quality presentations as a result of this class. So this is the example of the first case study, and then the other case study was on novel body antennas. And I don't have a picture here, but they did two cases, because these things, it's hard to build and it's not very easy to simulate either. But I want them to know that that people can be creative with basic elements as much as they want. So these arrays are very creative arrays to achieve a certain goal. So I wanted them to study or dig deeper into these ones, so that they get a big idea, or they get the bigger picture of how these things are being applied in a larger scale. And it's another one, like, so for extra credit, I want them to create an infographic. This one, it's an extra credit, so not everybody did that, but this is the best infographic I got on the smart antenna design. Just to keep things interesting, I gave different types of assessments over the semester. So in the first time implementation, so the pros of this method is that we merge hands-on exercises with traditional learning, and also they can visualize the results right after learning a concept. And the engagement is pretty high, because at some point, I think, even if a student works in a different field than RF or antenna field, still they got to learn a new software. And then for somebody who is willing to go for a job right after graduation, that was a plus. So I thought that the engagement was quite high as well. And since we are doing a lot of work inside the classroom, we are spending less time. So they had to spend less time outside of the class period, which is actually advantageous for me, because if I ask them to, like, if I post something to Brightspace and then ask them to watch it, there's no guarantee that they watch it or not. But if they are in front of me, if I play a video, they have to watch it. So I have more control of the classroom period. As well as there's a variety of activities and assessment techniques. So it made their life interesting as well as my life interesting as well. And also they gained proficiency of using a new software. In this case, it was HFSS. This is the one that we used for antenna modeling. And some of the disadvantages is that, at least for the first implementation, it's a lot of work for the instructor, because you have to prepare lots of things, like you have to order parts and then make sure you are ready for the real experimentation. And I kind of grew my work, so I prepared worksheets so that they have something to follow along. So it is more work, and also creating new assessments is also not always easy, but it actually keeps the life interesting. But at least during the first implementation, it's a lot of work for the instructor. But once you get on to the routine, then all you have to do is like small modifications. You don't have to do anything from scratch. So that's actually one advantage. But so as you can see, the pros of this outweighs the cons. So. And student feedback this time, I nailed it. So all good. I mean, knock on wood. In this one, I heard that, okay, this is good. It's the coolest class, although it's not here. One student told me that it's a great course, very informative, and they learned a lot. And then I'm famous as being high maintenance. I expect a lot, but they learn a lot. That's the point, because there's always, they had to learn to learn by because they're paying for the course, so they had to learn by taking a course. So it's not an easy pass. You do your work, you get a good grade, and then you learn something, and then you go and do bigger and greater things. So yeah, so this time all feedback was positive. So I was thinking, okay, then that means like I should apply this to other courses as well. And then some plus points. So last semester I had 2 students who took this course in the graduate level. So it was yearly 552. There was one additional requirement of submitting a conference paper. Another thing is, like, as I mentioned, we are primarily an undergraduate teaching institution. So our grad students, they are quite borrowed, like, because all our grad students, they are taking courses, they are registered at UMaine or RAW, about 3 hours up north. So they join only via Zoom. So, and this time I had 2 seniors, or last time I had 2 seniors who took the course in the graduate level. So Tyler Ellingwood, he actually submitted the conference paper. He already presented at American Society for Engineering Education conference at WPI last April, as well as, so I have another student, Zachary Myrtle. So Zachary, he got his paper accepted for the AMTA conference, which will be held in Westminster, Colorado. And he will be presenting this October. So the 2 students who took the course in graduate level, they both fulfilled their additional requirements. So this is something I also learned, like if you're dealing with undergraduate students, sometimes like research becomes their least priority. So you have to merge it with the class so that they get credit at the end of the class. So that's how, like, it's another strategy to get the research work done in primarily undergraduate institutions. So far it has been successful because not every undergraduate student would like to go for graduate studies. So we have to plant that seed. And then once they go for their first conference, then they get interested, and then they change their mind. But until then, we have to keep them going towards the research path. So these senior level courses are ideal to get those research output as well. So in future implementation, so right now I'm merging. So I have prepared my plasma engineering syllabus also, combining these hands-on experiments as well as virtual experimentation. And all these worksheets are currently published online for free. And because last time it was during the pandemic was still going on, and there were a lot of restrictions. People did not like having large groups in their companies, and also the campus had restrictions on students traveling in one bus. But like for future implementation, like the goal is to give them more hands-on experience, more real world examples. So I would like to take students to a large antenna array, and then last time I took about 4 students to HARP, but I would like to take the entire class to a class on a field trip or something. So, and I tried to go to a company, but they said like 20, like I had 25 students, so 25 is too big. So they did not like that. So, but these things, they go for future implementations. And so that's about the Alpha course, and I have some of the references, and here are my contact information, and thank you.
Okay, let's thank our Ashanthi. Very nice talk, and very probably most relevant to me is, since as in the associate dean position, I'm sort of in charge with looking at how we teach classes, and this actual emphasis on active learning is something we're really trying to push in all the departments. So in many ways, I wish we had more of our faculty and instructors listening to this talk, because a lot of these ideas of flipped classroom, which you mentioned, even though it's one you didn't fully use, but field trips, experiential learning is really the way that pedagogy is going, I think, not only here, but nationwide. So very, very nice to see a lot of these ideas and concepts, and that you've actually tested them. if I could ask two questions actually. One, so you started off by saying how the math can be a barrier, and there's other ways of teaching these concepts. Did you eventually bring the math in, Ashanti, or was it kind of left
Yeah,
out completely? Did the students leave the class with at least appreciating being familiar with those expressions, even though you didn't focus the teaching on them, or were they left out? And then if the other question, if you could also talk maybe what you said about the flipped classroom, I found very interesting. I've also been kind of hesitant about completely going that way, or asking all instructors to go there, even though there's a lot of enthusiasts about that method. If maybe you could say how much time in each class did you actually do the traditional lecture? Was it every day or once a week, or how much did you keep actual traditional lecture in this course?
Yeah, so the first question is actually a very valid question, because so I'm a math person, and I believe every engineer should know the math that they actually apply. So therefore, like, I actually introduced the math. So I always showed them the basic expressions, and then the most important expressions in class, and then some of the derivations. So we started off. So the first class, the basic parameter class, and for the infinitesimal dipole. So we used one class and then made it quite mathematical, and then did all the derivations. And then from that point onwards, in every class, I actually gave them the derived expressions, but we did not go through the full derivation, because if we go through the full derivation, I thought it might take the entire time. So therefore, I showed them. So I started off with the basics, and then sometimes I gave the intermediate steps and gave the full expression. Okay, for a dipole, the electric field is this. It's given by this expression. And then like for a different type of an antenna, this is the fully developed electric field expression. But we did not do the derivation in class. And always there are some students who are interested in more math. So for them, I uploaded more documents into Brightspace, so that if they are interested, they can go back and go through the full derivation. And also to answer the second question about like how much time, because so when I tried to apply the flipped classroom approach, when I created a small video and then uploaded that, but only 1/3 of the class has watched it. So out of 25, about 7 students has watched it. So therefore, and everybody else started watching the video in class. And that's when I realized it doesn't going to work that way, because then I can hear myself talking in everybody's computers. So then from that point onwards, I used to like teach for about 15 to 20 minutes in every class. Depends upon the example that we have been doing. So about 15 minutes, it's a traditional lecture on the board. So where I go through the introduction and then talk about all the things that they would need to carry on with the virtual experimentation. Yeah, so that's how it was done. And then the flipped classroom approach, it was not successful in my case. So yeah.
Very interesting. Any questions from the rest of our audience? I know at least 2 of the students enrolled in the seminar also do some TAing, so maybe some questions there, or from anyone else. And then if not, I'm going to ask a question to all the students.
Well, there's a question. It says, what kind of computer software do you use in this course? So in this course, we used HFSS. It's a industrial level. It's a high frequency studio suite. It's an ANSYS software, and it's actually so it's used in the industry. And that's the software I used. And then after the course, I think almost all the students could write HFSS certification. And for students who are trying to go for jobs right after graduation, having additional certification is a plus. So therefore, as I mentioned, like at USM, majority of the students, they intend to go for jobs right after graduation. And I have only like 2-3 students who wants to go for grad studies, but not right after. So yeah, so therefore, like, we used HFSS, and for Plasma course, I'm using MATLAB. And yeah, so for this course, it was HFSS.
Yeah, I think one thing to say about HFSS is very powerful software. I think very heavily used in industry, very expensive also.
Yeah.
So I think that's one software we did not, we still do not have at CU Denver here, but there's, I would say maybe about between 3 and 5 kind of packages that are widely used, and the HFSS is probably one of the more powerful. So that's great that your university supports using that cutting edge package. So.
Yeah, I think the reason being because mechanical engineering faculty, they use the other components of the ANSYS package, so we get it as a bundle. So.
Yeah. Any other questions to our speaker?
Hi, Ashanthi, this is Aditi. I'm just a new faculty here. I just joined this fall at CU Denver. So my question is, and I don't teach like very practical hands-on stuff. I teach more like modeling and like statistical modeling kind of courses. So my question is more about the software part of it. How do you develop? So for when I have taught earlier, I have actually provided the codes the day after I have asked them to code it so that they know what they're doing right or wrong. What is the best way to teach coding? So for example, if you're using MATLAB or if you're using RR Studio, how do you and this is not a programming class, right? This is programming is just part of solving a problem. So how do you actually effectively teach that?
So that's actually another good question. Let me go here. So that's another okay. So before going, I mean, if everybody at CU Denver, they're like my family, so I can be totally honest here. So I used FECO. In my graduate studies, and the only reason I switched to HFSS is because the campus already had the package. So when I actually, but in full disclosure, I was also new to HFSS. So I was like, okay, like how can I? So I have to. So I am learning the software as well as I'm teaching it. So I thought, okay, like this is a great point. So I should make a list of steps for myself. So that's how I actually started building the worksheets. And then after building the first worksheet, I'm like, oh, this is cool. So now all the steps were all there. So like to answer Aditi's question, and by the way, welcome to CU Denver as an alumni. I can welcome you as well. So these are the worksheets because the thing is like when students are learning a new software, so I had to learn it faster than
we don't see the worksheets, Johnny, if you're trying to show them. We just see the slide. You may have to.
Yeah, I have to stop the. So yeah, so you can find the link in my presentation as well. So these are all the help that I'm giving for the students. So I initially prepared the worksheets for me because HFSS has lots of moving parts compared to FECO, and all the students who, because I introduced FECO later on for different ones, we didn't have the full package of FECO. And these ones, like there are different steps. So every time I'm telling them, okay, like do this step and your output should look like this. So at the beginning, I gave a lot of at the beginning, I was giving a lot of help. And then later on, I thought, since I'm putting a lot of effort into this, why not I publish this as an online resource? And then because I can add that to my tenure package as well, hey, I published this. At the same time, I'm putting the effort anyway because I have to do it twice because I prepare the worksheets prior to the class. So I have to do the model and then I prepare the worksheets. I put that there. So in class, if I forget a step, people shouldn't miss a step. They have all the help they need. And also, even if they miss a class due to a valid reason, because at that time people were being tested positive for COVID and whatnot. So if they miss a class, they can still do it. They can still do it themselves. So to answer Aditi's question fully, like this is not a like learning the software is an added part. So we all have a big syllabus. We all have to teach a lot of theoretical content. And also we have to train them with the software. So I used to give them this help, and HFSS is actually a very graphical software. So I gave them step-by-step guidelines. Hey, do this first, do this next, do this next. So this is more like the gradual release. It's like the first time it the first time you observe what I do, and the second time you do it with me, and third time you do it with my help, and the last one you do it without my help. So towards the end, I didn't do this in class. I upload the worksheet and then I let them do it, because towards the end of the semester they had proficiencies of using it, so they finished their work. So it was the gradual release technique, and for me, having worksheets helped. Uh, having worksheets helped. And for the plasma class, since we just started the semester, right now I'm at the first stage. Like, they observe when I do it, and then after that they have to do it together with me. So they are simply following what I do on the screen. And then later on, I'll let them do it, and then I'll go walk around and help them. Towards the end, I'm removing my help altogether. So I just state the problem and they do it themselves. So yeah, so it's the gradual release technique. I hope I answered your question.
Yes, thank you so much. Like, this workshop technique is like really great. Thank you. Thank you so much. Yes.
Thank you. Yeah, it's a lot of work. You got to put double work, but still, yeah, it's worth it. Yeah.
Yeah, the best way to learn something is to teach it, right? That's
Exactly. Yeah, that's true. Because I was like, oh, I'm new to HFSS as well. And HFSS has lots of additional things to do, like creating a radiation space, this and that. So it's very easy to miss a step. So I'm like, I have to make sure that I don't miss any steps, so I don't get embarrassed in front of the class. So there should be a way for me to remember every step. So that's how I created the first worksheet, and that led to 10 more. So.
yeah, and I think it's very nice that you have the you have the theory, you have the simulation, and you have the hardware, right? I think those
Yeah.
three, that's a very powerful synergy there. So somebody walking away can really has had experience with all those three, and I can probably interview very well for a position if they can touch on all three of those. So. And any other questions from our audience? I'm really interested if any of the students just want to maybe not ask a question, but share feedback on maybe active learning techniques that you've seen in your classes. I know we have students from a range of departments, or maybe you haven't seen them, and maybe it could be that all your classes have been very traditional, which is not it could be both good or bad that way, but just interested to kind of see how the students are seeing this topic, and whether you've experienced it in your own learning.
Hi. So I would say, so I'm doing computer science. That's currently my major, and there isn't really as much of a physical aspect, I guess, in that sense, right? Like like designing antennas and stuff like that. But what I will say is that I've always found it really helpful when, for example, when someone's talking about like a concept in computer science, like memory management and stuff like that or something. And then I've always liked seeing them discuss like theory behind it, right? Which I think is always important to do. But then also like show, like there's a lot of like tools and stuff like that show like the actual computer memory, and then like how things are changing and stuff like that. And like coding it out live, and like showing like, I think there's something to be said about, like, even if it's still like at the end of the day software, right? It's not hardware. It's like seeing it running and stuff like that, and seeing like something actually being applied is like super helpful. So I think that even in computer science, like the same kind of stuff that was being presented today can kind of be applied. And then I used to be a TA for logic design. So they were like, it was like very intro level in terms of like circuits and stuff like that. But I know that kind of like walking through a diagram and stuff like that helps a lot of people understand things too. So yeah, that's from my experience.
Yeah, no, very, very good. I kind of liked how you touched on, like, where does where does the bit flip, or where's the information stored, right? I think in today's world where we're so hyper connected, right? I think it's important to know, where does information lie, right? Is it in the RAM? Is it on the hard drive? Is it in the cloud, right? What does that even mean to be on the cloud, right? And I now, as with young kids, they're just like, why doesn't the iPad work in the car? It's things like that really affect your life on many practical levels. And us kind of as engineers, we should always be kind of aware of those things, right? How does the system actually work? What inputs does it need to work? So yeah, it's very interesting what you said about teaching, visual kind of teaching of information flow, even in pure software. I think that's interesting. Okay, and any other feedback or questions? Okay, well, if not, let's thank our speaker one more time. Let her get back to work, since I know she's very busy doing great things. But really, thank you again, Ashanthi. It's been great having. I think the presentation was excellent, and it was even more excellent and impactful because of you kind of coming back home, as you said, as an alumni, as somebody who was trained and also taught here for many years. So we really appreciate you coming back and sharing this. So thank you.
Yes, thank you.